Hello, welcome back to the playlist of lectures on correlation, simple and multiple linear regression models. I am Hemakumar Kasala, and in this third lecture in the series, we focus on the topic of R-square, standard deviation, and the residual plots. Having understood as to how to arrive at the best fit least squares line or the regression line, this lecture focuses on methods to verify if the linear fit is the right one and arrive at measures to improve and verify the quality of the fit. Introduces the residual plot as a means to check if the linear fit is the right choice and eliminate influential data in the sample. Introduces new measures, namely R-square and standard deviation, in order to qualify the effectiveness of the least squares line fit. Let's get into the lecture. Assessing the least squares line fit that we discussed in the previous lecture involves verifying, in the first place, is a straight line the best fit for the sample data? Are there unusual data, that is, extreme values or outliers, found in the sample that needs to be addressed before concluding a least squares line fit? And when the regression passes the above two criteria, how best a fit is this line? How accurate we can expect the predictions to be using this regression line? The verification involves graphical and numerical methods. Almost all of these methods use the so-called residuals for the verification. Residuals are the differences between the actual y values and the predicted values y hat for each of the x values in the sample. Residuals equal y1 minus y1 hat, y2 minus y2 hat, and so on until yn minus yn hat, where y1, y2, and so on until yn are the n actual y values in the sample, and y1 hat, y2 hat, and so on until yn hat are the n predicted values using the individual x values x1, x2, and so on until xn from the sample. Therefore, residuals equal y1 minus a plus b multiplied by x1, y2 minus a plus b multiplied by x2, and so on until yn minus a plus b multiplied by xn, where b can take either a positive value or a negative value. Looking at the residuals graphically, residual 1 equals y minus a plus b multiplied by x1. Residual 2 equals y2 minus a plus b multiplied by x2, and so on until residual n equals yn minus a plus b multiplied by xn, where residual 1 is positive, residual 2 is negative, and so on, and residual n is positive. Residual plots, that is, the plot of the residuals versus the x values in their x residual pairs, help evaluate two of the three verifications we discussed to assess how best the least squares line fits the sample data. The first one being, is the straight line is the best fit for the sample data? And the second one, are there unusual data, that is extreme values or outliers, found in the sample that needs to be verified before attempting a least squares line fit? The first thing to verify in a residual plot is to look for any pattern in the residual plot, in particular any curvature. A curvature pattern as seen in this example indicate that the least squares line is not the perfect choice as a fit for the sample data. Let's understand the verification using a residual plot using an example. A sample of 15 individuals whose height in inches versus weight in pounds is provided here. The scatter plot is drawn for this sample data. The least square line coefficients are calculated, the predicted values are derived, and the least squares line is drawn. In the first look, the least squares line seemed to fit the scatter plot fairly well. Let's verify this observation using a residual plot. Residuals are calculated by subtracting the predicted values in the y hat column from the corresponding entries in the weight column. residual plot is constructed. The residual plot shows a definite curvature, suggesting that a straight line using the least squares method is not the correct fit for the sample data. Perhaps a nonlinear curve would be a suitable fit. We'll discuss the nonlinear curve fitting in the next lecture. Residual plot provides a better insight into the linearity aspect that a normal scatter plot between x and y fails to highlight. It's also important to identify the unusual observations, if any, in the sample data. The unusual observation can either be an influential observation that can exert excessive influence in determining the fit of the least squares line, or a large residual that can influence the fit to a certain extent. An influential observation is a one that can pull the least squares line towards itself, imparting a large influence on the fit of the line. Similarly, a large residual exercises a pull on the line to reduce the error. As you can notice in this example case, removing the influential observation from the sample data has resulted in a significant change to the fit of the line, as can be seen from the change in the coefficients of the regression line. The large residual observation in this case is not removed, since removing that data point does not prove to bring any significant change to the regression line fit in this case. The influential or large residual observations can be studied either from the residual plots or from the scatter plots as well. Whichever the method is, the influential and large residual observations have to be examined and removed if they exercise excessive influence on the line fit. Once the residual plots are examined for nonlinearity and the least squares line is confirmed to be the suitable one, and the influential and large residual observations, if any, are found or evaluated and removed where necessary, the next step is to evaluate how good is the linear fit given the dispersion of the data points. Does the line appropriately summarize the relationship between x and y? How good are the predictions for y made using the regression line for a chosen value of x? How to judge the accuracy in such predictions? There are a couple of statistical measures available to judge the goodness of the fit of the regression line. Let's explore them. What proportion of the variability in y is explained by the variability in x is one of the statistical measures that help qualify the degree of the fit that the least squares line offer. Slope b of the regression line, b equals r multiplied by sy divided by sx, where r equals correlation coefficient and sy equals the standard deviation of y in the sample and sx equal the standard deviation of x in the sample, plays a key role in determining the proportion of the variation in y that can be explained by the variation in x. What portion of the variability in y is explained by the relationship with x is given by variance in y explained by the virtue of the slope of the regression line divided by the total variance in y, which equals total variance in y minus variance in y left out, or in other words not explained by the regression line, divided by the total variance in y, which equals total variance in y divided by the total variance in y minus variance in y left out by the regression line divided by the total variance in y, which in turn equals 1 minus variance in y left out by the regression line divided by the total variance in y. Variance in y left out by the regression line is called as the residual sum of squares, denoted by SSR, is given by SSR equals y1 minus y1 hat the whole square plus y2 minus y2 hat the whole square, and so on until yn minus yn hat the whole square, which equals sigma yi minus yi hat the whole square. The total variance in y is called as the total sum of squares, denoted by SST, is given by SST equals y1 minus y bar the whole square plus y2 minus y bar the whole square, and so on until yn minus y bar the whole square, which equals sigma yi minus y bar the whole square. Proportion of the variability in y explained by the relationship with x is called as the coefficient of determination r square. Therefore, r square equals 1 minus variance in y left out by the regression line divided by the total variance in y. SST is the sum of the squares of the vertical distances of each y value with respect to its mean value. SSR is the sum of the squares of the vertical distances of each y value with respect to the regression line. Least squares line is fit in such a way that the residual sum of squares SSR is minimal. Substituting SSR and SST in the expression for the coefficient of determination r square, we get r square equals 1 minus SSR divided by SST. R square equals 1 minus sigma yi minus yi hat the whole square divided by sigma yi minus y bar the whole square. Coefficient of determination r square is the variation in y that can be attributed to an approximate linear relationship between x and y. The r in r square is nothing but the correlation coefficient between x and y. The coefficient of determination therefore equals correlation coefficient the whole square. Higher the value of r square, better is the fit of the least squares line. High value of r square is achieved when SSR is relatively small when compared to SST. Since the maximum value for r equals 1, the maximum value for coefficient of determination equals 1 square, which also equals 1. R square, which equals 1 minus SSR divided by SST, is the variance in y that is explained via the linear relationship. SSR divided by SST is the variance in y that cannot be explained via the linear relationship. While R square is one among the two statistical assessments that qualifies the fitness of the least squares line, the other statistical assessment is the standard deviation of the residuals yi minus yi hat. A high value r square does not guarantee always that the deviations of the individual observations are small with respect to the least squares line. There might exist a few deviations of significant levels, though overall measure of the deviations are small. Standard deviation of the residuals provides a typical amount by which an observation deviates from the least squares line. Standard deviation of the residuals, denoted by SE, is given by SE equals square root of SSR divided by n minus 2, which is equals square root of sigma yi minus yi hat the whole square divided by n minus 2, where n minus 2, that is the sample size minus 2 in SE, represent the degrees of freedom df given by df equals n minus 2, where 2 in df account for the intercept a and the slope b of the least squares line. Let's explore an example and understand the roles of R squares and SE. Here is the scatter plot and least squares line drawn out of a sample of 37 universities, wherein the graduation rate is plotted against the average per student expenditure over a period of 6 years. The least squares line computed is as follows. Graduation rate equals 17.68, which is A, plus 0.003837, which is B, multiplied by student related expenditure. R square calculated in this case equals 0.095, which is 9.5%. And the standard deviation of the deviations equal 12.0855. R square equals 9.5% suggests that a mere 9.5% of overall variance in graduation rate is explained by this linear relationship. SE equals 12.0855 indicates that the typical deviation about the least squares line is more than 20% of the range within graduation rate. R square and SE together suggest that the linear relationship between graduation rate and the student expenditure is not a very strong one, rather a weak one. On the other hand, scatterplot and least squares line from the same sample where the graduation rate is plotted against the median SAT scores for each university is as shown here. The least squares line computed is as follows. Graduation rate equals minus 70.69, which is A, plus 0.1127, which is B, multiplied by median SAT score. R square calculated in this case equals 0.447, which is 44.7%, and the standard deviation for the deviations SE equal 9.44933. Note that the value for B, which is 0.1127 in this case, is much greater than the student expenditure case where it was just 0.003837. R square equals 44.7% suggests that a much better percentage of overall variance in graduation rate is explained by this linear relationship. SE equals 9.44933 highlights that the typical deviation about the least squares line is roughly 25% less than the deviation in the previous case. R square and SE together in this case suggest that the linear relationship between graduation rate and the median SAT scores looks like a well-established one as compared to the previous case. That brings us to the end of the lecture on R square, standard deviation and residual plots, which is the third lecture in the playlist of lectures on correlation, simple and multiple linear regression models. See you soon back with the next lecture in the series. Bye until then.